Hey guys, it was so good to see you this morning in class, and I am just going to address a couple of practice problems from doing the entire stoichiometric process that you can go back if you are still needing help with today's homework. You can take a look at these tonight, or these will help you with an upcoming assignment that will be posted and due next week. Okay, so you can keep this as reference. You won't find an assignment attached here right now. One might be uploaded and connected to it later, or I'll link this video to that. That's probably what I need to do there. Okay, let me silence my phone. And let's get started. We're going to look at question number 21 on page 378. And this is the Haber process. So this is nitrogen reacting with hydrogen, making ammonia as as the product. And the question here says if 2.7 grams of hydrogen react, so 2.70 grams of hydrogen react, how many grams of ammonia will form? So this means, if you remember our process for working, if we've got our little diagram here, okay, this means we have grams. We're going to convert to moles using the molar mass of hydrogen, write the correct balanced equation ratios. Then we will have moles of ammonia, and then we're going to convert to grams. So let's do that real quick. Shouldn't take us but just a minute here to get this done. All right, so we're going to start. We start our math path with the question, with the data that's given to us here. Grams of hydrogen. We're going to convert that to moles. So I'm going to say 1 mole of H2 has a mass of 2.02 grams. So 2, there are 2 of them there. And then we're going to write our balanced equation ratio. All right, so the balanced equation says that there are 3 moles of H2. And then this is where I'm going. I didn't draw that while ago, but we're going down here and then over here and then back up, right? So we're going to land with how many grams up here. So 3 moles of hydrogen is in relationship in the balanced equation to 2 moles of ammonia. And if my question asked me for ammonia, then I would be done right there. But the question is how many grams, what mass? So we're going to keep going. And now we're going to say that 1 mole of ammonia has a mass of how many grams? So let's do that real quick. Ammonia is, we're using 14 for ammonia. I did not write that with my marker, did I? Let me pull my periodic table up here. Yeah, for sig figs, that's going to be all we need there. You could say 14.1 if you wanted to round that up for nitrogen. And then there are 3 hydrogens, so that's going to be 3.03 for all the hydrogens, so 17.04 grams of ammonia in 1 mole. Oh, did you guys see what I did here? I wrote that wrong. NH3. Got carried away. Got to talking to you and just got carried away. Now I'm ready to put my marker down and grab my calculator. So this is 2.7 divided by 2.02. I could say times 1, but that's an identifier, so I can just keep going. Times 2 divided by 3 times 17.04 equals, and I don't have to say divided by 1 because that just means the same answer, that would be give me the same thing. So I can only have 3 sig figs in my answer, so I can see here that my calculator is showing me a lot of digits, but I'm going to say 15, and that 8 is going to round that to a 2, 15.2 grams of NH3. So there's our final answer for that question. Okay, so another simple question, simple process there where we start with grams, convert to moles, use the mole ratio, and then come back out to grams. Now, I want to look at another question on this page. This question is, it says to list the 4 steps to solve a stoichiometry problem. So what you might want to do is, like, right now, pause and see if you can think of what you would do first, okay? The first thing we have to do is have a balanced equation. We either have to write the reaction ourselves, or if we're given a reaction. Remember, if a reaction has stoichiometric coefficients, we will assume that it is balanced. Nobody is trying to trick us here. What's the next thing we have to do? We're going to convert mass to moles. Remember, we saw that in our graphic. If we have mass, we're going to convert that to moles using the molar mass from the periodic table. That's going to be the moles of our unknown. The next step is to use the mole ratios to convert from moles of the known to moles of the unknown. And that, my friends, is what is happening right here. We know how many moles of this guy we have, but we must know how many moles of the unknown. So that's how we do that, using the mole ratio from the balanced equation. We don't care about any other mole ratio except the one that we're trying to solve at that particular time. And then the final step, of course, is to convert moles of the unknown to mass of the unknown, and that's what happens right here in this step. Now, do you see here, these 2 steps? They're inverses of each other. This is 1 mole over the molar mass, and this is molar mass over 1 mole. But what you have to remember is, this is molar mass of what's happening, of whatever compound we're talking about on this side, and this is molar mass of whatever we're talking about on this side. So we're going to have 2 different molar masses that we have to calculate because we are relating those 2 things, okay? So those are our steps, and those are the steps that we see here. This is the diagram. I have posted this diagram, or one that I drew for you, on Google Classroom, but I would encourage you to make your own so that you can color code it a way that makes sense to you, and you can reference that when you're working on these. Okay, so now let's look at one more problem before I hop out here, and this is going to be number, no, not that one. Here we go. This is going to be number 67 on page 393. So I've already written the equation here. This is chloroform. So here's the formula for chloroform, and it says this is a solvent, and it's produced by a reaction between methane and chlorine. And so it says, the question says, how much methane, question mark, how much methane in grams is needed to produce 50 grams of chloroform. Now, I picked this question because I want to bear out to you the important fact that stoichiometry is so powerful because it does not matter where my information is. I can use that information to answer a question about anything else in the balanced equation as long as I have one piece of information. Even if, and this is actually really good in industry because we might sometimes like when we're cooking, when you're cooking, you're like, oh, I have this many things, like I have 2 potatoes, so how much potato soup can I make? But sometimes the way you come at a recipe is I need to feed, in the products, I need to feed 50 people. If I need to feed 50 people, how much food do I need to get, right? So it's a different question, but we can answer the question if we have the correct information. So let's work this one out real quick together, and then I will get off here and let you reference this. So of course, here, let's just draw this. So here we're going to what? Convert to moles, and then we're going to find moles of this, and then we're going to come back out and be able to find grams. So you see how our little graphic is going to keep us on track. So 50 grams of chloroform. Okay, 50 grams of chloroform is what I want to produce. So remember our steps? What's the first thing we do? We are going to convert this to moles. So 1 mole of chloroform has a mass, and I have already calculated this over here, but I'll show you real quick. I'll put it here so you can see it. It's one carbon as 12.01. I'm going to use 12.01. We'll get a little bit better, cleaner answer here. And then one hydrogen is 1.01. 3 chlorines. Each chlorine is 35.453. So that gets us 106.36 when I multiply, right? 3 times this for a total mass of 119.37 grams. That's grams per mole of chloroform, sorry. Now we're going to do our balanced equation ratios. So I'm just going to look up here at my balanced equation ratios. Some of you are going to want to not write these words. But here, guys, I didn't mark out anything on that other one, did I? Bad form, Fraser. This is where the magic happens. You might say, well, I see in the equation that it's 1-to-1. But this is where we change the words. So 1 mole of CH4. That's what we don't know. That goes on top. And then I want 1 mole of CHCl3, right? That goes on bottom. Now, we get rid of the words that we don't want anymore. Now, we want to do the molar mass. So 1 mole of CH4 has a mass of, let's do that again, it's 12.01, and that will be a 5 there. 12.01 for 1 carbon, and 4 for each hydrogen is 1.01, 4 hydrogens, 4.04, 16.05 grams. Now, once that's all filled in, let's get rid of words. There we go. I should cancel those with a different color. Now, let's grab our calculator and see what we get here. 50, so what do we do? Divide, because it's in the basement. 50.0 divided by 119.37 times 1 divided by 1. I don't have to do anything there, right? Times 1 divided by 1. You don't have to do anything, right? Equals, but I'm not done. Now to go do this. Times 16.05 equals, I had something hanging out my calculator wrong. I apologize. 50 divided by 119.37 times 16.05. I think I missed a decimal there. There we go. So the correct answer here then, this equals 6.72. I can have 3 sig figs grams. Now grams of what? Grams of methane. So now we can see how in industry, if you needed to make a certain amount of chloroform, you would know exactly how much methane you had to have in order for this reaction to take place. And then if you could also calculate the amount of chlorine that you needed to make exactly 50, because what would we do? We would just change the mole ratio here and put in the molar mass for chlorine. We can find out everything we need to know. It's a really powerful concept, stoichiometry. I hope you're having fun with it.